Hello. Today we're going to talk about the rank of a matrix. First, let's review some concepts since we're going to need some results in what we'll discuss today. Let's say that V and W are vector spaces, and T is a linear transformation. Remember that the zero vector in V maps to the zero vector in W, that is, T of OV equals OW. The subset, capital N of T, that consists of those vectors x that map to the zero vector in W is a subspace of V. Moreover, we'll say that our linear transformation T is one-to-one if and only if this N of T is the trivial vector space. The subset R of T, which consists of those vectors U in our codomain W, such that U equals T of x for some x in the domain V, is a subspace of W. Moreover, the linear transformation T is onto if and only if R of T equals the codomain W. This subset N of T is called the null space of T or the kernel of T. The subspace R of T is called the range of T or the image of T. The nullity of T is the dimension of the null space, and the rank of T is the dimension of the range. The dimension theorem asserts that for any linear transformation between two finite dimensional vector spaces, then the nullity of T plus the rank of T is the dimension of the domain. Let's continue to denote V and W as two vector spaces, but now say that V has a basis beta and W has a basis gamma. We have a map phi sub beta that takes a vector x to its coordinate vector. That is, these will be the scalars after we write our vector x as a linear combination of the vectors from beta. This phi sub beta is a linear transformation. Similarly, given any linear transformation T, there exists an m by n matrix A that makes the diagram above commute. The idea here is that a linear transformation that sends a vector x in the domain to T of x in the codomain really just corresponds to matrix multiplication on the coordinate vectors. The map phi sub beta is called the standard representation with respect to the basis beta, and the matrix A, which we'll denote by square bracket T, is called the matrix representation of T in the ordered bases beta and gamma. The following three statements are equivalent for a linear transformation between two vector spaces V and W. First, there exists a unique function U going from W to V such that the compositions T circle U and U circle T are the identity maps. Second, T is both one-to-one and onto. And third, the rank of T is equal to the dimension of V is equal to the dimension of W. Any linear transformation T satisfying either of these properties is said to be invertible or an isomorphism. In this case, we will say that V and W are isomorphic. The function U, as above, is called the inverse of T, and we'll denote this by T to the minus 1. If T is an isomorphism, then so is T inverse. And in fact, the statement V is isomorphic to W really defines an equivalence relation on vector spaces. Let's review a very specific application when our vector spaces V and W are finite dimensional. Recall that script L of VW is a vector space. It's defined as follows. The elements of LVW are linear transformations from V to W. Addition of two linear transformations is that linear transformation that sends a vector x to T1 of x plus T2 of x. Scalar multiplication is that operation that takes a linear transformation T1 and a scalar c and returns that linear transformation that sends a vector x to the vector c times T1 of x. If V has a basis beta consisting of n elements, then our standard representation gives an isomorphism from V to the n-dimensional vector space f to the n. Similarly, If W has a basis gamma that consists of m elements, then the standard representation gives an isomorphism from W to the m-dimensional vector space F to the m. L of VW is isomorphic to the collection of m by n matrices by using that map that takes a linear transformation T to its matrix representation square bracket T. In fact, if T, our linear transformation, is an isomorphism, then the inverse of the matrix for T inverse is just the inverse of the matrix square bracket T. The idea here is that we can replace any finite dimensional vector space V with just F to the n. We no longer have to deal with an abstract concept. We give a quick example to illustrate all of this. Let's say that V and W are the real plane R2, and let's let beta and gamma denote the standard basis. Recall that we can write a linear transformation in the form you see here on your screen in terms of some 2 by 2 matrix A, B, C, D. Let's assume for the moment that AD minus BC is non-zero, and let's consider the transformation U that you see here on your screen. Then U is actually the inverse of T. The 2 by 2 identity matrix is that matrix in the form 1, 0, 0, 1, and it satisfies A times I equals I times A equals A for any 2 by 2 matrix A. And finally, the inverse of our matrix Q, which is the matrix ABCD at the top of the screen, is just the matrix we found for U, namely D minus B minus C A, each of the 4 entries divided by AD minus BC. And here's our last concept for review. Let's say that A is now an M by N matrix. Recall that that means it has M rows and N columns. There are 3 types of operations that we can perform on the rows. Type 1 means we can interchange any 2 rows. Type 2 means we can multiply any row by a non-zero scalar. And type 3 means we can add a scalar multiple of any row to another row. These are called the elementary row operations. We have similar definitions if we replace the word row with the word column. An elementary matrix is an n by n square matrix, which is obtained by performing exactly one of these 3 elementary operations on the n by n identity matrix. Let's say that A is an m by n matrix, and suppose that B is obtained from A by performing one of these 3 elementary operations. First, if this were a row operation, then B equals E times A, multiplication on the left, for some m by m elementary matrix E. Second, if B comes from a column operation, then B is A times E, multiplication on the right, by some n by n elementary matrix E. Third, elementary matrices are invertible. And in fact, the inverse of an elementary matrix is a matrix of the same type. We remind you how the argument here goes to prove this. Let's denote E superscript PQ as that square matrix where the only non-zero entry is 1, and this appears in the pth row and qth column. Then we can multiply E superscript PQ times A on the left and similarly on the right. Here, we would simply find a matrix if we multiply on the left, where in row P, we would replace row Q of A. If instead we multiply on the right, then in column Q, we would place column P of A. We're now ready to discuss the new concepts for the day. We'd like to first start off by discussing left multiplication by matrices. Let's let V be our n-dimensional vector space Fn, and W denote our m-dimensional vector space Fm. we'll write beta and gamma as the standard bases for these two vector spaces. Given an m by n matrix A, we'll define a linear transformation L sub A as follows. It will simply take a vector x and return A times x. This linear transformation is called the left multiplication by A, or the left multiplication transformation. Hence the reason why we write this as L sub A. Observe that if we have this linear transformation and consider the matrix representation with respect to these standard bases, then we just recover our matrix A. We'll define the rank of an m by n matrix A as the rank of this linear transformation. Remember that that means it's the dimension of the range of this linear transformation. Let's say that A is an m by n matrix. Then A is invertible if and only if both m equals n and the rank of A equals n. Say that A is the matrix representation for some linear transformation T. Then the rank of T equals the rank of A. Finally, let's say that B equals P times A times Q for some invertible matrices P and Q. Then the rank of A equals the rank of B. In particular, similar matrices have the same rank, and elementary operations on a matrix are rank preserving. Let's start by showing the very first statement. Since A is an m by n matrix, then our left multiplication transformation maps from Fn to Fm. If we'll denote beta and gamma as the standard bases for these two vector spaces, then recall, as we said before, the matrix representation of LA is just the matrix A. We saw before that A is invertible if and only if the left multiplication transformation is invertible. But we found from before that a linear transformation is invertible if and only if its rank equals the dimension of the domain equals the dimension of the codomain. However, the dimension of the domain is n, the dimension of the codomain is m, so we must have m equals n. Also, the rank of the left multiplication is by definition the rank of A, so we see that this double equality holds if and only if both m equals n and the rank of A equals n. Now let's show the second statement. The idea here is that we're going to stare at various parts of the diagram that you see above. We're going to pay particular attention to the rightmost column, this arrow corresponding to phi sub gamma. Let's denote W0 as the range of T. This is a subspace of W. This will be a subset of the upper right-hand corner of this diagram. We'll also denote Z sub 0 as the range of the left multiplication transformation. This will be a subset of the lower right-hand column, the F to the M, which we'll also denote by Z. We're going to prove that phi sub gamma, the standard representation, is an isomorphism between W0, which is a subspace of W, and Z0, which is a subspace of Z, which is F to the M. To do so, we need to show three statements: that phi sub gamma, the specific map, is well defined, it is one-to-one, and it is onto. Let's start by showing that it's well defined. This means that if I take an element from W0, then phi sub gamma should return an element in Z sub 0. But this is a matter of simply staring at the arrows. For example, if U is an element of W0, then remember that U must be an element of the range. So U equals T of X for some X in V. This is in the upper left-hand corner of the diagram. But now, by the composition of maps, we see that we can either map from X using T at the top of the diagram and then down using phi sub gamma. In the same way, we can also map down using phi sub beta and then over to the right using L sub A. So our x and v will then map downwards to square bracket x sub beta, and then of course this maps over using LA to an element in Z. But by staring at this a little bit more carefully, we see that our phi sub gamma of u really does lie in Z0, the range of left multiplication. Now let's prove that our map phi sub gamma is 1 to 1. But we already know that this is true because we proved in the previous lesson that phi sub gamma is actually an isomorphism. You can see a slightly different proof here on your screen. Finally, we'll prove that our map phi sub gamma is onto. This means given an element z in our Z0, we must show that z is equal to phi sub gamma of u for some u in W0. But again, this is a matter of simply staring at the diagram that we had on the previous screen. So now we've proven that there is an isomorphism between W0 and Z0, showing that the range R of t is indeed isomorphic to the range of L of A. Now, we simply compute the dimension of our spaces. Recall that the rank of t is by definition the dimension of the range of t, but this is also equal to the dimension of the range of L of A. But by definition, this is the rank of A. So we have indeed shown that the rank of A is indeed equal to the rank of a transformation T. Let's show the third statement. We're going to consider a slightly different diagram from the one we had before. Here, the intuition is to write a matrix B, which is P times A times Q. We can either write B as coming from this left multiplication map that you see at the very bottom, the L sub B, or we can travel starting at the lower left, go up to the upper left, go over to the upper right, and then go down to the lower right. This composition here of these three arrows does correspond to multiplication by Q, then multiplication by A, then multiplication by P. Remember that composition always goes from right to left. We're going to show that Z0, this is the range of L of A, this is a subspace of the upper right-hand corner, will be isomorphic to Z sub 1, the range of L of B. This is a subspace of the lower right-hand corner. Both of these will be subspaces of Z, which if you recall is F to the M. We're going to prove that left multiplication by the matrix P is our desired isomorphism. First, we'll show that this map is well defined. Let's take an element lowercase z that is in Z0. That just means that it's in the range of left multiplication by A. Using pretty much the same argument that we had in the previous slide, we'll look at our element z as it sits inside of z to the m in the upper right-hand corner. LP of z, of course, now says that this sits in the lower right-hand corner. But by following along the arrows in a couple of different directions, we actually do see that this really must come from an element u that sits inside of the lower left-hand corner, and now we just simply push everything through as we expect. Next, we'll show that this map is 1 to 1. Well, if LP of Z1 equals LP of Z2, then simply put, P is an invertible matrix, so we can multiply P on both sides to find that Z1 does indeed equal to Z2. Finally, we'll show that our map L sub P is onto. Let's take an element lowercase w that lies inside of Z1. Recall that this is the range of L sub B. The argument is very similar to before in that we simply look at the four arrows in our diagram and just move around until we find an element z that we desire. The intuition here is that our element u, lies in the lower left-hand corner as before. So now we've proven that Z0 is isomorphic to Z1, that is, the range of LA is isomorphic to the range of LB. But now the rank of A, which is by definition the rank of L of A, is just the rank of LB, which is by definition the rank of B. Let's now finish the last part of the theorem. Let's say that A is similar to B. This means that there exists an invertible matrix Q such that B equals Q inverse times A times Q. But if we use the proposition we had before where we denote P equals Q inverse, then we do see that the rank of A is equal to the rank of B. Finally, let's say that B is obtained from A by some elementary operation. Well, then this means that either B is obtained from A by an elementary row operation or by an elementary column operation. In either case, we can write B as E1 times A times E2 for some elementary matrices E1 and E2. But we also know that E1 and E2 are invertible, so using the previous proposition with P equals E1 and Q equals E2, we again see that the rank of A is equal to the rank of B. Thanks very much for listening.